Let's talk about stability and weight and balance, the fundamental theory behind weight and balance. Now, on an aircraft, it's all about the balances of weight and therefore forces that oppose weight. So you can have it in the pitch axis, right, around the lateral axis. You can have it around the longitudinal axis or the roll axis, and you can even have it around the vertical axis or the yaw axis. As student pilots, we generally only care about it around the lateral axis and how the weight is distributed along the longitudinal axis, because we usually have, the same amount of fuel in both wings. We're usually not carrying any payloads on our wings like missiles or anything. So the weight on our wings are usually the same. So we're usually balanced from left to right, but what changes is where we load, if we have passengers here, baggage back here, or how much fuel we have. So that's usually what we care about with weight and balance and stability. For this stability, it's all about the balance between 2 points. Now, one point is the force going down, and that would be the force of gravity. So the weight of this aircraft, where this total weight is applied, is called the center of gravity. And that's going to be a point somewhere along this longitudinal axis. Then the point we compare that to is the opposite force of weight, which is lift. So that's the force we get up. And that center of all our lift created by the wings, the tails, anything else on the aircraft is called the center of lift or center of pressure. Now, so that's going to be where we can apply the entire total lift force on one point. Now, where those line up along the longitudinal axis, so you have the center of gravity somewhere on here, and then you have the center of pressure somewhere on here. Where those line up determine your longitudinal stability on your aircraft. And that's what weight and balance is all about. When you have a distance between the center of pressure and the center of gravity, that is called a moment arm. Now, if you've calculated weight and balance before, you know that you find a moment by calculating the weight times the arm, or the moment arm. So without a moment arm, the aircraft would be perfectly balanced. To demonstrate this, I just have this ladle. Now, obviously this side is going to be heavier, right? So it got more mass over here. You would expect, if it was the same weight distribution, I could balance this right in the middle, but look at that, it tips towards the heavy side, right? So I have to move my finger over just a little bit. If I were to be perfectly still, I could get it to balance right around here. The center of gravity must be right around here. And what we're doing with my finger is essentially what the aircraft is doing with all the lift. So we can think of the point where my finger meets this ladle as the center of pressure or center of lift. Now, when I match that up with the center of gravity, I'm able to balance it. If the center of gravity is forward to this side of the center of pressure, if I move the center of pressure here, it's going to tilt down, because now we have a distance. So we have a moment arm between the center of gravity and the center of pressure. We have an arm distance, and that creates a moment towards the center of mass, which causes the moment force to tilt this in that direction. So this is the same thing with aircraft. If we were to place our aircraft when it was empty, right, on the empty weight CG, right on a giant finger, we would be able to balance it. Now, when we're flying, it's different, because our force is not a finger. Our force is created by airspeed, and it's created by our wings and our tail a little bit, and it's called lift. Where does that center of pressure end up? Well, actually, aircraft engineers and manufacturers, they design the aircraft so that the CG is forward of the center of lift. Usually the center of lift is somewhere along the wings here, and then the center of gravity is going to be forward of that. So again, just like the ladle, we have a moment arm, and a moment is going to want to naturally pitch the aircraft this way, pitch down. Now, why do they want the aircraft to pitch down? Well, this is where we get into stability. When the aircraft has a center of gravity that's forward of the center of pressure, giving a pitch down moment, the aircraft is more stable. And there's two types of stability. There's static stability and there's dynamic stability. Static stability is the ability for the aircraft to initially go back to equilibrium. So let's say we're flying here on straight and level, and we get some turbulence, which causes us to pitch up, right? So a bump of turbulence, we pitch up, and then what happens is, because that center of gravity is forward of our center of lift, the aircraft is going to want to immediately pitch back down. So that immediate initial action is called positive static stability, because it immediately goes back towards where we want it to be. Now, if we only had static stability, it would go past our equilibrium of level flight, and then it would go back up, and it would just kind of be in this oscillation. Now, that's where dynamic stability comes in. That is the ability of your aircraft when you have positive dynamic stability of your aircraft to reach your equilibrium point, your level flight point, over a period of time. So what it does when you have dynamic stability, these oscillations, if you just had positive static stability, it dampens these oscillations until finally you're in level flight. Now, we talked about how the center of gravity in front of the center of pressure causes us to get positive static stability. So how do we get dynamic stability? Well, that's all about the tail. Now, it changes depending on the aircraft, because not all aircraft have tails down here. Some have high T tails, some have, wide tails. So it depends on the aircraft. But in general, what happens is the tail kind of it provides a little bit of lift, right? Or it provides, less lift in certain times. And the way aircraft are designed is that when we get these oscillations, the tail is going to counterbalance those with a little bit of force, lifting force that it's creating, and it acts as a damper. So it dampens these oscillations until you have, again, steady flight. So again, the CG ahead of the center of pressure gives us positive static stability, and then the tail acts as a damper over time, which gives us positive dynamic stability. To bring it all together, why we want to find where our CG is, because we generally know our center of pressure changes depending on what we're doing in flight, right? Depending on our angle of attack, depending on whether if we have flaps deployed, our airspeed, things like that, how much lift we're creating. So it's going to change, but the engineers generally know a range of where that center of pressure can be. Then, therefore, know a center of gravity or a range of centers of gravity where we want to be at in order to remain stable. And that's all you're doing when you find the center of gravity, and then you look in the CG envelope and you make sure your center of gravity matches your weight within that CG envelope. That envelope is exactly this. It's that range of outcomes and distances between our center of gravity and our center of pressure over all envelopes of flight. Hopefully that helps you guys out a little bit in understanding the weight and balance theory.